Good afternoon, everybody. I hope you had a good lunch break. I'd like to introduce you to this session, Digital Twins and Simulation Modeling for Large Warehousing Operations. STEYN is the speaker this afternoon, and he's a supply chain analyst at DSV Global Transport and Logistics. He's part of the supply chain innovation team, and he specializes in operations research and a number of other things. He has an honours degree in industrial and systems engineering from University of Pretoria. And I thought this was interesting to add that through the course of 2020, LLEWELLYN began expanding DSV's capability with regards to simulation modeling, with the aim of using simulation to develop and maintain digital twins of DSV warehouses in South Africa, to reduce strategic and operational risks and to improve operational excellence. Please ask your questions in the question and answer session, and we'll have a discussion afterwards. And thanks, LLEWELLYN. Over to you.
Thank you, Claire. Welcome everyone to this presentation. I'm really excited to be here today, and feel quite privileged and honored to present to everyone today. And before I kick off, I'd just like to congratulate SAPEX on a wonderful conference so far. I haven't attended all of the sessions, I'll admit, but I'll definitely be catching up on them over the course of the next couple of days. And it almost feels like the real thing, despite the fact that this is a virtual conference. So as Claire mentioned, I'm a supply chain advisor at DSV. A little bit of background about DSV. I'm sure everyone is familiar with the business. We are one of the largest third-party logistics companies in the world. Depending on when you measure us, we'll either be the third or the fourth largest, usually after DB Schenker, DHL, Kuehne and Nagel. Where I fit into the DSV picture, I'm a supply chain advisor in our supply chain innovation team locally. So we do a host of different exciting things. Our sort of flagship service offering to customers, both internally and externally, is inventory optimization, which is a long-standing perpetual service that we've been offering. We also do a lot of work on supply chain network design and optimization, supply chain segmentation, and that sort of thing. And as Claire mentioned, something that we are looking into and have been looking into over the past year is simulation modeling and digital twins, specifically with regards to warehousing operations. Our supply chain innovation team falls within our sort of warehousing division, which we call solutions in South Africa. And so that's really what I'll be discussing with you today. So I hope everyone can see my screen. I'm going to just start off by explaining just on a really high level what I mean when I use the term digital twin. So I'm going to do that by just telling a short little story. Last week, a couple of colleagues and myself flew to Kathu in the Northern Cape. So Kathu is a tiny little mining town in the Northern Cape, close to Sishen, which is an Anglo-American mine, and we were there for a project. Now, of course, because Kathu is such a small town, it has a really small airport. And because it has a really small airport, you fly there on a tiny little aircraft. If you're lucky, it's a small jet plane. If you're not so lucky, it's a small aeroplane with a propeller. And the fact is, no matter how seasoned you are as a flyer, you do get a little bit jittery climbing onto a small aircraft like that. And that's exactly what happened to me last week. And I was sitting there thinking to myself, it's amazing that you sort of entrust your life to a pilot. I mean, pilots do go through very rigorous training. They write all kinds of tests and exams. They have to do frequent medicals. Generally, a pilot will have to spend years flying smaller aircraft until they can actually do commercial flights. But the fact of the matter is, if you've ever seen any sort of air crash investigation documentary or anything like that, you'll know that when a disaster happens, it's never a single variable that sort of causes the accident. It's always a series of unfortunate events sort of strung together that result in a aviation disaster. And even with years of experience, a pilot is unlikely to encounter any of those variables in their sort of day-to-day aviation activities. Maybe they'll encounter engine failure once in a career. Maybe they'll encounter really bad weather once in a career. And that really sort of poses a problem to the aviation industry, because how do you actually develop strategies to get out of a bad situation if you can't really expect a pilot to encounter those situations often? And the aviation industry actually solved this problem years ago with a digital twin. And that digital twin is commonly referred to as a flight simulator. And the idea behind it is a flight simulator is really an abstraction of reality. It's not exactly the same as the real thing. You're not going to get the same adrenaline rush, the same feeling as when you're flying a plane. But it's actually close enough that you can put pilots in those situations, and they can actually learn to deal with those issues and find the best strategies out of them, and it's safe. No one gets hurt in a flight simulator situation.
Llewellyn?
Yes.
I'm sorry to interrupt you. I'm not sure that you're sharing your slides, because we can't see those to pin them.
My apologies.
No, that's my apologies. You were just in such a great story that I didn't want to stop you.
No, thank you for stopping me. The same thought that occurred to me, but there you go. That's a flight simulator. It's a digital twin designed to mitigate risk for the aviation industry. And so really what we did at DSV last year is we sort of built a digital twin of our own, specifically for the same reason, to mitigate risk. And the risk really came from three separate areas. The first is that we had built a new facility. So just to take a quick step back, DSV globally follows a growth strategy of acquisition. So we acquire a lot of our competitors, and sort of a byproduct of that process is we often sit with site duplication. So once you've acquired competitors, you have multiple sites in the same area that perform the same functions. And to solve that, we do site consolidation. And so as part of that strategy, we actually developed a site that we basically just finished called DSV Park Gauteng. Yesterday, there was a fascinating presentation by the project manager, Morna Jansen van Rensburg, on that particular project. And if you haven't seen it, I would urge you to go and look at that. So we had a new facility. As part of that new facility, we also got a new customer on board. And that customer plays in the FMCG space, which is relatively new for us. So if you take sort of those three variables together, we felt that we needed to provide a higher burden of proof on our solutions design. And for that reason, we actually went for a simulation modeling approach. So just sort of on a high level overview, the project that we undertook, initially, we were really just focused on answering a simple question from the customer, which was, do you guys actually have enough doors on the inbound side of your warehouse? And obviously, we did an Excel calculation, and we thought we did, but we wanted to be sure. And so we built a simulation of the inbound part of the warehouse, all the way from unloading through to pick and drop and put away. Having seen the benefit of that inbound simulation, we decided to also model the outbound side of the warehouse, so all the way through from storage to dispatch. And of course, once we had an inbound and an outbound model, might as well put the two together and sort of create a digital twin of the entire customer's operation. So that's just on a high level the project scope of the project that I'm going to discuss with you today. So I'm going to take you on a quick digital tour of the facility. It's a video. The quality isn't great, but I think you'll probably get what I'm trying to show you. So I'm just going to show you sort of the infrastructure. So it is a massive warehouse, 90,000 square meter warehouse, but we were in particular concerned with the part on the bottom right where our new FMCG client was going to go in. You can actually see the racking here. The racking is transparent so that we can actually see what happens within the racking, MHE and so forth. The new customer are a consumer healthcare client. So this right part of the warehouse here is actually an OTC chamber, over-the-counter medication, SAPRA approved, Schedule 0, 1 and 2 pharmaceuticals go in there. And then this part on the left here is sort of your general consumer healthcare goods, you know, the sort of stuff that you would find typically in a Clicks or a Dis-Chem. The simulation was built on the actual AutoCAD file that we used to design the facility. It's to scale. Everything is essentially a digital twin of the facility. as we designed it prior to go live. So that's sort of the inbound side. I'm quickly going to jump over to the outbound side. So again, you're just looking at a 3D version of this simulation that we built. Over here, QC and repacking. Because this client is in the pharmaceutical space, quality control was quite an important aspect to the project. What you'll also see here is the actual pick face. So we modeled this in a lot of detail. You can see the different colors here. These are all different pallets in the pick face. And that is, of course, because picking is such an important warehouse activity. So hopefully this just gives you an idea of what the 3D world looked like for this project. Of course, the real sort of work sits in the background. We mapped all of the processes that the customer's materials would flow through the warehouse, customer requirements, all of that was mapped in, and the model actually went down to a shrink level on the outbound side. So we actually modeled this, this warehouse activity prior to go live in a great deal of detail. Okay. So once we actually had the model, like a flight simulator, we could use it to test a whole bunch of different scenarios. And to do this, we actually got some really, really rich input data from the customer, which we were fortunate in getting. They provided us with a year's worth of inbound data and outbound data, really detailed. We could sort of infer the vehicle type on inbound. We could infer the order lines on each ASN. We knew exactly when that vehicle arrived, so we had date and time stamps on the data, which was really useful. On the outbound side, same level of detail. We had literally an entire year's worth of order data down to the order line level, exactly which SKUs. We had really good master data, so we could see SKU dimensions, and all of that we incorporated into our model. Of course, we built this model prior to go live. So a challenge for us was actual activity times. So generally with simulation modeling, you'll do something like time studies to actually see what your processing times would be. And of course, we didn't have access to that because the facility didn't exist and the customer wasn't our customer yet at that point in time. But luckily, we are a third-party logistics company, and so we actually have a database of activity standards, right down to sort of the base process level, something as simple as how long it takes for a forklift to put a pallet on its forks. So we actually used that to model the processing times, and we added some distributions on that just to sort of inject some variability into the model. Because we had this whole customer data set, we could actually select days that we wanted to run in the model, days or weeks, and say, listen, what is the worst day we could possibly encounter? Take that into our model, see how our operation reacts to it, and make the necessary changes prior to go live. So given those inputs, we could also obviously produce a bunch of outputs. So of course, an important piece of information is resource utilization. You want to make sure that your utilization is just right. You don't want to over or underutilize your resources. So we could see from the model what our resource utilization was going to be on MHE, on staff. We were also interested in facility utilization. So as I mentioned before, it's a massive facility, 90,000 square meters. So we weren't that interested in utilization in terms of actual racking space. We were comfortable that we had enough space there. We were more interested in our shared spaces, staging space, repacking space. All of that was modeled as well. Of course, in any sort of operation like this, throughput is crucial. So we could actually model our throughput on receiving, what's our turnaround time on vehicle offloads, dock to stock, all sorts of KPIs like that. We could also model on the outbound side our pick rates, how fast we can process returns and so forth. And all of this really just fed into sort of operational success KPIs that we could then use to see where our bottlenecks were and stuff prior to go live. So I'm just going to take you through a couple of slides on a high level, just to demonstrate sort of some of these outputs to you. So what you're looking at over here on the bottom is a snippet from the simulation. As I mentioned before, right at the beginning of the project, we were very interested in how many doors we would need for this particular client. They push really large volumes. You can get 30 trucks a day coming in, for example. And so we wanted to make sure that we would have enough door space and staging space. So here you can actually just see in the model the forklift offloading pallets, staging space, etc. And on the top, this is the sort of graph we would produce. So throughout the course of the project, we probably produced between 30 and 40 scenarios. And for each scenario, we would produce a graph, something like this. So you could actually see on this graph how many doors you have available during the course of the simulation run. These are on-grade doors, so side-loaded doors over here, and these are dock doors. And as you can see throughout this particular simulation run, you don't have that many dock doors available. And so this is really just the sort of deep insight that we could gain prior to go live. As I mentioned before, resource utilization, crucial. So this is just another snippet from a slide I presented through the course of the project. This is on the inbound side, forklift utilization, EPT utilization, reach truck utilization. Are we over or underutilizing our resources? What are the strategies that we can implement to improve our utilization prior to go live? And then on the right-hand side, we actually have utilization over time. So because we got such a great data set from the customer with timestamps in, we actually spent a lot of time looking at volume fluctuations between inbound and outbound. So this sort of became important when we joined the inbound and outbound models to actually see, can we move resources around? Can we use some resources dedicated to inbound, or should we share them with outbound? And as your volume fluctuates throughout the day, we used figures similar to these to actually guide us in our decision making there as well. Pick rates, also an important variable in the FMCG space. If you ask your FMCG customer when would they like you to deliver their order, they'll tell you yesterday, right? So picking is a crucial aspect to any warehousing operation, but particularly within FMCG. Of course, there are various variables that affect picking productivity and efficiency, and these were all taken into account. And we could actually then produce figures like this for each scenario, saying exactly what our pick rate was going to be and whether that pick rate was sufficient to deal with the large outbound volumes that our customer expects of us. I think just for a moment, I'd like to draw your attention to these figures on the right, just to sort of illustrate some of the advantages of simulation modeling. So these are distributions. This one on the bottom right over here is a distribution of vehicle travel time, low-level order picker travel time through the racking. Typically, if you are designing on a spreadsheet, you're using an average or a median. You'll probably be designing on a number sort of over here. And really, that doesn't tell the whole story. If you are designing on an average or a median, you aren't encapsulating all of the tail end of the distribution. And it's similar to my flight simulator analogy. Aircraft crashes don't happen on an average day. They happen at the tail end of the distributions when things go wrong. And the same for any operation. And really, with simulation, you can actually see the tail ends of the distributions. And it's these tails that sort of cause problems for an operation. So another interesting use of the simulation, and this was sort of accidental. As I mentioned before, FMCG picking is crucial. We knew that prior to go live. So one of the projects that ran in parallel with this project was a slotting project. Slotting just refers to the optimal location of products within the pick face so that you can actually minimize travel distance through the pick face and maximize picking productivity. Because we had the simulation and because the simulation was so detailed in the sense that we actually modeled the pick face down to the shrink level, ties and eyes on each pallet for each particular product was modeled in the simulation. We could actually take the results that a consulting company gave us, slotting results, and we could actually pull that into our simulation to validate those results. So yeah, you can just see sort of picking activities taking place, and that really was sort of an upside of the simulation project that we didn't anticipate prior to kicking off the project. Another interesting slide that I always enjoy sharing is congestion. So this is not something that we've really explored very deeply, but I think there's a lot of potential here. The simulation modeling software that we use at DSV, FlexSim, allows you to draw heat maps on the go quite easily. And these heat maps sort of show you which areas of the facility might experience congestion. So again, in the FMCG space, you have very many resources traveling throughout the pick face. And the hypothesis here is that congestion could potentially reduce picking rates, for instance. So this is just the outbound side of the warehouse. On the bottom left here, you have the OTC chamber for the pharmaceuticals, over-the-counter pharmaceuticals. And here is actually the consumer healthcare pick face. And as you can see, a lot of congestion in and around the pick face, around the fast movers. So this is just an interesting slide I always enjoy sharing. There's a lot of deeper analysis we could probably do on this to actually look at pick faces being blocked and perhaps even exploring the possibility of having slotting configurations where you don't necessarily bundle all your fast movers together, where you spread them out to reduce congestion. So those are just sort of high level, some of the outputs we produced throughout the course of this project. I hope you found them interesting. I thought for the last sort of 8, 9, 10 minutes of my presentation, I would delve a little bit into our experiences with simulation modeling, and then also just look at the differences between simulation modeling and digital twins. So any tool is never perfect. It's never a silver bullet. And so I thought it might be interesting to share where we see simulation modeling being applied in our own business. What sort of projects are appropriate tools for, or appropriate for the simulation modeling tool, and what sort of projects are inappropriate for this particular tool. So when is simulation an appropriate tool? I think the example that I just showed you of the simulation we built for an FMCG client sort of falls into these first two categories, where problems require a higher burden of proof. So where a traditional spreadsheet-based approach is not sufficient in terms of the burden of proof required, simulation really does provide the depth required to solve those types of problems. The second one sort of falls into my flight simulator example, planning for uncertainty and reducing risks. So as I mentioned before, risks generally are a lot of variables coalescing at once. And using simulation, you can actually stress test your system, which is also something we did. Basically test, for instance, what happens if you have the biggest inbound and outbound day occurring at one time. If you have fewer resources than you were planning on, what exactly happens to the system? And then having actually seen how your system reacts, you can actually plan and try and investigate sort of risk mitigation measures for those risks. And of course, it's a safe environment to do that without actually stress testing your actual operation. This middle category is traditionally where simulation models have fallen into. If you're an industrial engineer at varsity, you would have probably come across this sort of simulation. We're using simulation to look for efficiency improvement opportunities. So, standard simulation approach would be model an existing system, validate it, find the bottlenecks, and then try and improve efficiency in that system. And that would sort of fall within this space. This, again, very traditional use of simulation modeling, exploring big what-if questions. Something I'll touch on in a little bit is simulation, despite the improvement in the technology over the past couple of years, remains a relatively slow tool. So it is very well suited to sort of big what-if questions, capital expenditure projects, for instance, where you have long lead times, relatively large budgets, and you actually have the time to build proper simulations to validate your decisions. So this, again, is sort of traditional simulation use over the last couple of years. Last one, there are many analytical tools available to us nowadays. You could build simulations in R and Python, open source coding software. You'll get exactly the same results as you would in a visual system such as FlexSim that we use. However, the visual aspect of any simulation really wins stakeholder buy-in for your ideas. I've seen this myself with this project. whether the stakeholders are senior management or whether they are your customer. Actually seeing the live visual 3D environment just creates a sense of trust. And in that sense, it is a brilliant tool. Simulation is not always the appropriate tool. For me, projects with rapid implementation requirements are not appropriate for simulation. Maybe that's because I personally don't simulate fast enough, but I have found that you need long lead times to build a good simulation model. And if you need answers and you need them now, it isn't very well suited to simulation. The second one, sort of generic projects where variables are predictable and well understood. I think the point I want to make on this is that simulation, in my opinion, remains a tool for the exceptional problem, not for the day-to-day problem. Again, because of the long lead times required, it's generally quite resource intensive. You're going to have to buy a license. You're going to probably have to have an engineering resource spending time building the model. And if you can solve something on Excel, by all means, do it. We have many operations that still use spreadsheet-based tools, and they perform very well. So simulation is the exception, not the rule, in my opinion. So these last 2 points sort of push us towards the realm of digital twins. Projects with a multitude of unknowns. So in any project, there is going to be unknowns. However, the number of unknowns is an important factor to consider. Generally, standard simulation approach is identify the question that you want to answer, identify the variables that relate to that question, control for those variables, and build the simulation around that, having made a certain number of assumptions. However, if your number of unknowns is exponentially sort of getting bigger and bigger, you end up having to make more and more assumptions, and the more assumptions you make, the poorer the quality of the simulation. In that sense, we move towards a digital twin where you are actually trying to encapsulate the whole system. You aren't necessarily trying to answer a specific question. You're trying to replicate an entire system and take sort of all the possible unknowns into account. And again, digital twins, and I'll elaborate on this a bit later, a lot more complex and a lot more time and resources required. The same sort of goes for this last point. Traditional simulation use has pretty well predefined goals. There might be many goals in a simulation modeling project, but they are predefined, versus on a digital twin where you're actually replicating a system and using that digital replica to answer questions as they arise. I thought it might be interesting just to share with you for a minute where we see simulation fitting into the warehousing lifecycle. So this is, of course, on a very high level. Generally, the life cycle starts with sales. Customer approaches us for a warehousing solution, or we approach them, probably the latter in most cases. We design a solution. Some of that design will take place during the sales process. We go live with that solution. Any go live is going to be tricky to some extent. After a while, you stabilize the operation, and eventually you reach maturity. And then a couple of years down the line, you renegotiate and you start the process all over again. So the project I described to you today falls solidly within the realm of solutions design. And as I mentioned before, mature operations, very traditional use of simulation, existing operation, model it, find the bottlenecks, improve it. An interesting thing that we've been discussing internally is using simulation modeling and digital twins as part of the sales process. So the idea would be, and this would be particularly applicable to our multi-client facilities where we have more than one client under one roof. The idea would be maintain a digital twin with all of the customer's data, fresh data that you're constantly maintaining. When you actually encounter a sales lead, you take that potential customer's data, you plug it into the digital twin. You use that to demonstrate capability to the customer to say, listen, this is our current operation in this warehouse. This is where you would slot in. This is how your operation would work. And we can actually demonstrate that we can meet your operational KPIs. And in addition, you have that visual aspect. which is very beneficial to the customer. And we could even go as far as using that for costing. So that is something we've discussed quite a bit. Operational stabilization and go live, I think, is where simulation becomes difficult. Generally, in a go live, you need to remedy any issues that occur rapidly. And as I mentioned before, simulation is not a rapid tool. So that is sort of an area where I see difficulty using simulation in our warehousing life cycle. I think before I conclude and take some questions and open up the floor for discussion, I want to just elaborate on the evolution of simulation models to digital twins. So throughout this presentation, I've sort of been using the term digital twin and simulation model interchangeably. They are not the same thing, in my opinion. The technology is progressing such that we are moving from simulation models towards digital twins. And really, the difference is I've identified sort of 4 variables that differentiate between a simulation model and a digital twin. You'll find that the project we embarked on, in some sense, fall under simulation, in some sense, fall under digital twin. But really, it sort of comes down to frequency of use. Standard simulation approach is find a question, build a simulation, answer the question, leave the simulation in the back of the cupboard, never to be seen again. A digital twin is something that is meant to be used all the time. It's meant for repeated use. The implication of that, of course, is that the model needs to be consistently maintained. So you need someone to actually constantly update and validate the model. In terms of input data, technology has progressed significantly. The software that we use, for instance, allows you to pull data via SQL directly into the model. So the idea would be that you actually pull live data into the simulation, run scenarios on the simulation. That data goes back into the operation, and it actually affects the operation on a monthly or a weekly or even a daily cycle. And that would be a true digital twin. Application. So I think I touched on this somewhat 2 slides ago. Simulation, generally predefined goal, whereas with a digital twin, you're actually trying to replicate a system, and you don't necessarily know what the problems are that you're trying to solve prior to model development. So what becomes crucial in the development of a digital twin is you need to replicate the system exactly as it is. And then as you're running the model and you're maintaining the model and issues happen in the live operation, you have the digital model to quickly solve those problems and give that feedback back into the operation. And then, of course, output data, which sort of talks to the other 3 points in terms of frequency of use. So those are my personal thoughts on simulation modeling and digital twins, and I hope you found this interesting. And I would love to hear your thoughts and open up the floor to some discussion.
Thank you, Llewellyn. That was very interesting. You had lots of likes, especially on your slide on the simulation model that highlighted the congestion. And we've got about 5 questions. So I'm going to start at the top from Yash. Nice, Llewellyn. How long did it take to create the simulation, and how accurate is it versus reality?
Okay, so on the first question, it took long. I didn't do this full time, but the project probably ran between June last year and March this year. How accurate is it versus reality? There's a quote that our MD used recently in a meeting that says, no plan survives first contact with the enemy. So we changed a lot of the design literally 4 to 6 weeks within after go live. So difficult to say at this point. We went live in April and we're still stabilizing. So yeah, I hope that answers your question.
Great. Amanda, were there any changes to the facility or the operation that you introduced as a result of the insights gained from the simulation?
Yeah. So I think something I missed out that I was planning on saying is the simulation sort of followed the design by sort of 8 to 12 weeks. So the design would come up and say, listen, we need this many MHE. We'd plug it into the simulation, see what happens, and that would then influence the design. So yeah, there were a couple of things that did change as a result of the simulation.
Great. Thanks, Llewellyn. Is there a level of tech maturity that a client would need to be at to use this, or can it be modeled with available data? Which I thought was a great question.
Very good question. So I think you need good data. You probably need an ERP system. Our client was on SAP, which means we got timestamps out of everything. Timing is important in any operation. It's not just about capacity. It's also about when you need the capacity. So in that sense, I would definitely think you need quite a bit of tech maturity. There are ways around it. I mean, standard second-year industrial engineering is to go and do time studies of an operation. Sometimes that is still what's required, and you could build a very valid simulation using an approach like that.
Great. Celeste says, excellent presentation. Thanks for the feedback, Celeste. Was there a need to optimize a specific model parameter using OptQuest within FlexSim? I hope you understand what that is, Llewellyn, because I don't.
I do. So that is not something that we did with this project. We are familiar with the technology, and we want to use it. I personally would love to use it for slotting, right? As I showed on that slide. I mean, FlexSim at the moment, which is the software we use, is so advanced that you can basically build a replica of your entire storage system in the model, right? So you can have the exact addresses, the sort of bin types. If you can put certain products in certain bins, you can build all of those rules into the model. And I can definitely foresee that you could use the optimization package that comes with FlexSim to actually solve for a slotting configuration. So yeah, I would love to look into that more as well, definitely.
Great. Thanks, Gerard. Tertius, how many people are skilled to develop and maintain the model in your business?
So that is a challenge as well. We have a lot of people that have done FlexSim training, that have done simulation training, but you kind of need a dedicated resource for this sort of modeling. It's very difficult to do it with part-time resources. Generally, our continuous improvement engineers are trained on this technology, but you find the closer you get to an operation, the more time you spend putting out fires, the less time you spend thinking strategically and building the model. So I think, within supply chain innovation, we are trying to expand our capacity. Because we are better suited to that. We aren't that close to the actual operations, and we can take a step back and spend the time to optimize. So the short answer is lots of people are trained on it. Few people have the time to actually do it.
Okay, excellent. Thanks, everybody, for all your engagement. We have a couple more minutes if there are any other questions. And while you're contemplating that, please can you go to the polls tab and rate the presentation for us? We'd appreciate the feedback. Celeste is asking, how long did the project take?
So kickoff was June last year, all the way to March this year, but not full time. So I'd say a model of this type would probably take between 3 and 6 months to build.
Excellent. Thanks, Llewellyn. What great work you're doing.
Thanks for having me. I really enjoyed this session.
Thanks, everybody. And if you would like to chat to Llewellyn further, just look out for each other on the attendee list, and then you can meet in the lounge and have a real chat with your cameras and microphones on. Don't forget that facility. And a reminder that all the presentations are recorded, so if you want to come back and look at one of Llewellyn's brilliant slides at a later point, have a look at our YouTube channel, and a link will be sent to you in the next week or so on that. So thanks again, Llewellyn. Thanks, everybody, for your engagement, and enjoy the rest of the afternoon and the SAPIS conference.
Thanks.